And welcome back to the workshop, to this workshop dedicated to a new horizon in dispersive hydrodynamics. And so then we can start. So it's my pleasure to introduce the first speaker of the day, Pierre Suret from Université Lille. And he will talk about integrable turbulence and soliton gas, experiments and theoretical approaches.
Thank you very much for the introduction. Do you hear me? Everything is fine? Yes.
Yes, we can hear you. Yeah.
Okay. So everybody, hello everybody. Good morning, good afternoon, or good evening, depending on where you are in the earth. Thank you very much to Gennady and all the organizers of this very nice online conference. And I hope that next year we will all meet in real life in Newton Institute. So I will speak about soliton gas today, and I will speak mainly about experimental and numerical results and trying to show how this concept can be applied and used in real life, I could say. Soliton gas is part of the field of integrable turbulence. This word has been introduced more than 10 years ago by Zakharov, just to name the combination of random initial condition with an integrable system, integrable PDE, such as one-dimensional nonlinear Schrödinger equation, KDV, sine-Gordon. And despite the fact that we have the tool of inverse scattering transform to find exact solution of this integrable PDEs, the problem of initial conditions that are random together with IST is still an open question. Okay, so the idea of integrable turbulence is to look at the system with random waves. And soliton gas is one example of integrable turbulence. So I will try to explain why in a few minutes. So in my talk, I will have two questions. First is, can we generate controlled soliton gas in real life experiments? And the second question is, this concept of soliton gas, can it be useful to understand natural phenomena such as the modulation instability? Okay, we'll take the example of modulation instability and show how soliton gas can help to understand statistical properties of modulation instability. So, as you probably all know, solitons in integrable system experience elastic collision. So it means that if you take two solitons and you look at the collision of these two solitons, what you get in the long-term evolution is just a shift, phase shift and a space shift. And the solitons after the collision recover their shape. You can easily see it when you do just numerical simulation of nonlinear Schrödinger equation, but of course you have full theory of solitons from the 70s and 80s about this collision. The idea of soliton gas has been proposed in the 70s by Zakharov. He has introduced diluted soliton gas for KDV as just a large ensemble of random solitons. So it means a large ensemble of solitons on an infinite line with random parameters. And of course, the solitons experience this well-known elastic collision. Many years after that, Gennady and after that, Gennady and his co-author have introduced the concept of dense soliton gas. And things are a little bit different now because it means that you cannot separate solitons in your mind, saying, okay, I put one soliton and then another soliton. And the key concept of the theory of soliton gas is then the density of state that correspond to a probability density of solitons having some spectral parameters in the inverse scattering transform framework. So lambda will be my discrete eigenvalues in my talk. And so this density of state means that you have a given number of solitons, but actually of discrete eigenvalue per unit length. And at the core of the theory of soliton gas, you find kinetic equation, and you see that they have the form of continuity equation this is related to the fact that eigenvalues are constant of motion. So you preserve the total inverse scattering Fourier spectrum, sorry. And the key point is that here the velocity S is non-trivial, and it is given by an implicit equation in which you have the phase shift here that depends on the spectral parameters and the velocity that you find in the integral and outside. I will not speak about the detail of that, and I'm sure that Alex Tovbis in his talk tomorrow is going to give probably a lot of details about the rigorous theory of that. What I want you to remind in my talk is that the key concept is this density of state, which is the density of eigenvalues. So in literature, in experimental literature, in particular in nonlinear optics, you can find in the 80s and 90s the word soliton gas used in papers, but actually completely disconnected from the concept of soliton gas proposed by Zakharov. It is just the word that is there. And to the best of my knowledge, the first paper in which you have the use of this word soliton gas related to what has been done in the theoretical paper is this paper from the group of Nicolas Mordant in collaboration with Miguel Honorato, in which they have demonstrated shallow water soliton gas by using the fission of soliton, which is a Zabriskie-Kruskal mechanism when you launch long sinus wave in a water tank. After some propagation, after some time in the water tank, what you observe is many waves that can be identified for some of them as solitons. And what is important that in this paper, the analysis that is used is the linear Fourier analysis. So they plot and they measure this dispersion relation, and you can see that you have straight lines that are signature of the existence of solitons. So in this first paper on soliton gas, there is no measurement of the density of state, okay? And in our group, what we do experiments in optical fibers. This is a picture of our lab because we are in a lab of optics, but we also work with people from hydrodynamics, and in particular, people from the École Centrale of Nantes in France, Félicien Bonnefoy and Guillaume Ducrozet, and the group of Eric Falcon in Paris. And we try to do experiments in both configurations to investigate integrable turbulence. And even if in this talk I don't speak about that, we have also done experiments with Miguel Honorato. So when you compare optical fibers experiments and water tank experiments, at leading order, they can be described when it's deep water waves in water tank and when it's anomalous dispersion in optical fiber and single mode optical fibers. It can be described by the focusing one-dimensional nonlinear Schrödinger equation. So for theoreticians, be careful. In most of my talk, the propagation variable is z, which is a distance of propagation, and in the second derivative is the time. And this describes the slow varying amplitude of the electric field or the surface elevation. And interestingly, physically, the typical scale of propagation, the length of propagation are quite similar, hundreds of meters. But of course, the time scale in optics are much smaller, okay? And because of this very small time scale, some of the measurements in optics are very difficult. And I will say one word about that in a few slides. So, question that I want to address first is, how can we build an experimental dense soliton gas? So dense soliton gas means that we will use the concept of soliton gas that you can find in the paper of Gennady, in which the key concept is the density of state. So one of the things that you need to do is to make a choice for the boundary condition. And the most natural when you do an experiment is zero boundary condition, because you will switch on your experiments and you will stop it at some point. So you will not have, for example, periodic boundary condition or a non-zero boundary condition. So it means that the framework immediately is inverse scattering transform with zero boundary condition, in which you can have a continuous spectrum or discrete spectrum. And because we focus on soliton gas, it means that we will consider only this discrete spectrum. And then everything is characterized by the eigenvalue that are constant of motion and the norming constant that evolves quite trivially with the propagation distance z. Okay, so to build a soliton gas in this framework means that we will build an n soliton with some characteristics of the eigenvalues and the norming constant. So somehow what we are doing is to use the n soliton solution that are exact solution of NLS as a model of the soliton gas, okay, that can be defined theoretically on an infinite line, for example. So the last ingredient that we can put is the fact that if you want to look at a stationary soliton gas that will probably emerge naturally in some experimental condition, if you look at a very long propagation, the natural thing will be to put random phase for the norming constant. So it means that what we can do to model a soliton gas in real world is to compute n soliton solution with n very large, using a density of state, which is a distribution, statistical distribution for the eigenvalues, and put random phase for the norming constant. So even if the formula are known since the 70s, it is only recently that it has been possible to compute this solution for large n and even just to plot them. And this has been possible by the work of Gelash and Agafontsev, and they have shown that by using some dressing methods, so like a turbo transformation, an arbitrary precision technique numerically, you can compute n soliton solution by any distribution of lambda that you can choose, and of course random phase of norming constant for n very large, so it means hundreds typically. Okay, so this is an example of this n soliton. Right, so now we have a tool to build in real life a soliton gas. So this is an example of what we have done in the water tank. This is the slow varying amplitude that is computed by the technique that we have told you. These are the eigenvalues that we have chosen, put random phase, and in red, you have the wave themselves. Okay, so you multiply this slow varying amplitude by the carrier wave. And here you have the evolution of the slow varying amplitude as a function of the propagation distance. The time here is a retarded time, which means that you see we take into account the group velocity at the carrier wave frequency. And what you observe here, the two colors in this IST plane, so real part and imaginary part of the eigenvalues, are the IST or the direct scattering spectrum computed at z equals 0 and at the end of the water tank, so at the last gauge, which is 120 meters. And you see some small difference. And here, what you see is the change in the IST values during the propagation. So all the colors here correspond to different Z of propagation. So what you see is that the IST spectrum in experiments is not perfectly preserved, of course, because an experiment is never exactly integrable, but you see that more or less we are able to preserve the structure of the IST spectrum. And here it's a simulation taking into account high order effect to show that these effects are due to high order perturbative effects that are not taken into account in 1D NLS. So here it's an example with only 16 solitons. And of course, if we want to have soliton gas, we need to go to very large number of solitons. And this is an example with 128 soliton. And now we have many solitons. So now we can define a density of state, which is a probability density function of eigenvalues that you can compute as a function of real part and imaginary part. And here what you observe is the evolution of this density function during the propagation. And here the full Euler equation. So again, you see that our measurements show that we preserve more or less the density of state, but you see some small change because of high perturbation effect. So this work shows that it's possible to make a soliton gas in real world, and that the concept of density of state also will give you some signature of the influence of high order effect that breaks slightly integrability in experiments. Okay, now I will answer to the second question, which is this concept of soliton gas, the theory of soliton gas, can it be used to explain, describe, and understand physics that exist naturally, okay, or exist in many experiments? And I will take the example of the so-called modulation instability in the focusing one-dimensional nonlinear Schrödinger equation. In hydrodynamics, it's called Benjamin-Fair instability. And the idea is that if you take a deep water wave train, purely monochromatic, if you have a small sinus perturbation, for some of the frequency of this perturbation, you will have instability. So it means that the psi bond in the Fourier space at this frequency of the perturbation will increase exponentially. The spontaneous modulation instability, what it is, you start from a plane wave. So if I look at the envelope of this plane wave, it's a constant, and you just consider some noise. So it can be even a white noise if you want, but very small compared to this plane wave. And the spontaneous modulation instability is the fact that you have a gain spectrum in the Fourier space, and all the Fourier components that are inside this gain spectrum will grow exponentially. So here you have the spatiotemporal evolution when you start from a plane wave, so a constant background, and you have destabilization, and now you have some noisy structures, and you can see here the movie, and this is a Fourier spectrum. So this is a fundamental phenomenon because nonlinear Schrödinger equation describe many systems, and in all the system you have noise. So this phenomenon is very unknown, for example, in nonlinear optics and in photonics community. It's only quite recently that the statistical properties of this phenomenon has been fully described by numerical simulation, and this has been done by Agafonsev and Zakharov in 2015. And here are the main characteristic signature of spontaneous modulation instability. First, if you look at any statistical moment, so here it's it is the linear part and nonlinear part of the Hamiltonian, you have a transient regime with oscillation, and you go toward a stationary state. So of course it's a stationary state in the statistical sense. So it means that the statistical properties at long-term evolution reach some stationary feature. Here you have the stationary spectrum, Fourier spectrum, okay, with this exponential tail, this kind of maxima here, and this peak in at zero frequency. And what is really remarkable is that the long-term statistical properties of one point, if you look at the probability density function, it's a Gaussian statistics for the field, for psi, for the real part of psi, and which means that it's an exponential statistics for the modulus square of psi, that we call the power in optics. And this is the stationary state of the long-term evolution of modulation instability. So the modulation instability has been widely investigated in nonlinear optics, and in particular in optical fibers. And I don't have the time to describe anything in detail, but the thing is that it's important to know that it's only the last years, because of the big improvement in the ultra-fast measurement in optics, that it has been possible to observe in single shot the field. So to observe phase and amplitude of the field, and also to observe the spatiotemporal evolution in the fiber. So just to summarize very briefly some experimental results, here what we have done is we use what is called a recirculating fiber loop. So it's not a resonator, but the light do many loops in this fiber loop, and we can observe at each round trip, we can observe the field, and with this we are able to reconstruct the spatiotemporal evolution of the dynamics. You see that in experiments we get this Fourier spectrum that I've shown you in numerical simulation, and we can see all the properties that I've described to you. So again, because it will be important for you to have that in mind, at long distance of propagation, exponential distribution for the modulus square of psi, some oscillation, for example, here of the kurtosis, which is here the second moment of the power, or the fourth moment of modulus of psi, oscillation that goes to some stationary state. And also, finally, something that I haven't said up to now, if you look at autocorrelation of the power, you will get some remarkable oscillatory structures, okay? And these oscillatory structures of this autocorrelation physically just correspond to the fact that here you have some given time scale. Okay. The thing that here it's numerics and experiments and there is no theoretical description. So I promise you to try to address this question with soliton gas. So again, the question is the question of boundary condition. We'll use exactly the same thing than before. Theoretically, the problem of modulation instability is on infinite line. If you do numerical simulation, you use periodic boundary condition. Here I will truncate. So I will use a very large pulse of length L0 with some noise. And what I'm saying is that at some fixed given time, if I look in the central part of this guy, I will have the same statistical properties than this guy. If I look at the problem of noise going to 0 for the amplitude, we go actually to almost a box. And the eigenvalue, the IST eigenvalue of the box are well known theoretically since the 70s. Here I've put, there is an exact formula that is implicit. Here I've put an approximation of this exact formula in the semi-classical approximation, just for the sake of simplicity. So what I have is that the modulation instability, I propose to model it by a box with some very small noise. I know the IST eigenvalues of this problem. So it means that or if I speak about a soliton gas, I know the density of state that I will compute in 1 minute. And the only thing that will remain is if I want to look at the long-term evolution, I will put some random phase for the numbing constant of this guy. So about the numbing, the density of state, you take the eigenvalues of the box and you look at the number of eigenvalues that correspond to a given eigenvalue. So sorry, the number of discrete points that correspond to a given value of the eigenvalues. And what you get is the Vries distribution. And probably Alex Tovbis will speak about that tomorrow, I imagine, in his talk. But Gennady and Alex have shown that this Vries distribution corresponds to a critical density of the condensate in the theory of soliton gas. So we can build, as in the first part of my talk, we can build n soliton, exact n soliton solution by taking this spectrum, put in random phase, and we do that with the technique of André Gelache, and we get this guy. But what is remarkable is that now we can look at the spatiotemporal evolution of this guy and compare to modulation instability that start from a plane wave in nonlinear Schrödinger equation. We can look at the value of the linear and nonlinear Hamiltonian that are in dashed line here and compare the value of linear and nonlinear Hamiltonian of my n soliton with the long-term evolution of modulation instability, and it perfectly match. And look at that now. This is the comparison between simulation of nonlinear Schrödinger equation by starting from a plane wave with some small noise and average over many of my n solitons build with my recipe. That is, I take this eigenvalues and I put random phase of the numbing constant. And you get a remarkable agreement for the optical spectrum, so the Fourier spectrum, the statistics, and what is called the G2 function, which is the autocorrelation. They perfectly match. So what does it mean? It means that you can describe the long-term evolution of the modulation instability in the framework of the theory of soliton gas. Just very briefly, very recent results in the PhD of Giacomo Roberti and Alexandre Lebel. We can measure phase and amplitude in our lab of the field. So it means that when you record this modulation instability, you recognize here, you could even think that it's numerical simulation because you have the field, you can compute inverse scattering transform of this guy. You can do many experiments and compute the statistics. And what Alexandre and Giacomo have found is that you get indeed in the experiments of modulation instability, this distribution, this Wiles distribution as a density of state of your soliton gas. So thank you very much. To conclude, the take-home message is that soliton gas is very exciting and that it can be applied to experiments, that it can be useful to understand the physics, but of course now there are many things to do. And one of the things is to try to have a full theory combining statistical approach and inverse scattering to describe integrable turbulence. I would like to acknowledge all my collaborators. I will not have the time to name all of them, but of course, all this work has been a lot inspired by the work of Gennady, Andrei Gelash, and I would like to point out the important role of the PhD student. So Giacomo Roberti, who is still a PhD, Alexandre Lebel, who is still PhD in our group, and previous former PhD student of our group, Alexei Tikan, Rebecca El-Koussefi, and Adrien Krech, who are doctor now, but a lot of things that I've presented in my work own a lot to them. Thank you very much.
Thank you, Pierre. Thank you for your talk. Very, very interesting. So we have time. We have time for questions. So I see there are already questions in the chat. So two questions from Daniel Ratliff from Northumbria. So first question, in the experiments, so I guess it's a water wave experiment. In the experiments, do you see recurrence like in your small movie, or do you see downshifting like in the water wave tank experiment, like the paper of UN at collaborator?
Okay, extremely good question. Recurrence, when we speak about modulation instability, so it's about modulation instability or not? Or is it
so I guess I can jump in and ask. Yeah, so it's when the wave train goes unstable, you can either have two occurrences happen. You can either have this recurrence where it goes back to being uniform again of the same wave number or close to, or like in the experiments of Ewan and Lake, you can see that the wave number drops, so the waves spread out and they get slightly larger.
So about the recurrence first, about the recurrence. This really depends on the size of the noise, okay? So typically in optics, you have both kind of publication. You have publication in which people look at recurrence. So in this case, it means that they put a strong sinus perturbation, strong compared to the natural noise. Here in experiments, we don't put any perturbation. It is only the natural noise that comes from amplifier and the source. And when you have noise, there are no recurrence. And from the theoretical point of view, my view on that is that the recurrence has an infinite period, if you want, because you have many modes in the noise. Okay, so in what I'm showing here, there are no recurrence at all in any of the experiments. Okay, because we are dominated by noise.
Yeah.
Okay, so that's one of the things about the downshifting. So there is a bit of downshifting. In any, I have also modulation. I haven't spoken about that, but I have also modulation stability in water waves. Here you see it. So you see that there is a bit of velocity here. Okay, and this is due to the downshifting, due to the high order effect. Okay. So indeed, when you look in detail in water wave experiments, you have downshifted due to high order effects. And in optics, you can have quite the equivalent, which is due to Raman scattering. But in optics, we are able to do very narrow Fourier spectrum. So we are able to do experiments in which we are very well described by NLS compared to water waves.
Yeah. Thank you. Yeah, that explains a lot. And fantastic talk, by the way. Very engaging.
You also had another question, I think, Dan, no? Or...
Yeah. So I was going to follow that up with, do the soliton gas models capture this kind of downshifting as part of their statistics?
It's one of the open questions for me, because you see, I know only a few papers in which they look at perturbation of IST due to high order effect. There are some old papers, okay, but I'm not specialist of that. So it would mean that you would need a IST theory with perturbation due to the high order effect and look at the influence of that to the density of state. It's one of the questions that I sometimes ask to Gennady. At some point, I think it's one of the things that we have to do, okay? It's to put high order effect, do perturbation, and what is the influence of density of state? But at the moment, I think nothing has been done in this direction.
Yeah, it's a very hard theoretical problem, even at the water waves level, to theoretically analyze it. So yeah, thank you.
And we also have a question from Rémi Dubertrand. Is it possible to also simulate the diffusion of a soliton gas and maybe address localization phenomena?
I don't know what it would mean, diffusion of soliton gas.
Yeah, Rémi, maybe if you can turn on your microphone.
Right, so if we take the analogy of the soliton gas being a gas of particle, and if you put them in a sort of disordered environment, then you will, I mean, for classical particle, you would start to see diffusive dynamics. So that was the spirit of my question.
Okay. So if strictly speaking, if you speak about soliton gas, it's integrable system, you have only elastic collision. So what can be thought about is collision between two different gas, for example. You can find that in some paper of Gennady. I don't know if I have any picture somewhere. No, I don't have it here. But you can find in the paper of Gennady, maybe I can show it like that. I'm sure I have something somewhere just to make understand what, yes, here. So you see this kind of experiment. This is numerical simulation in which you have a shock of two different soliton gas.
Right.
So we could imagine experiments in which, at least conceptually, in which you have two gas and one which is really random and the other one with a sharper distribution, for example. Look at that, this kind of thing. But it would be collision of two soliton gas.
Right. Well, and then in the same spirit was that, can you have a control of the disorder amplitude, for example, to start reaching Anderson localization regime?
I'm not sure there is a connection with Anderson localization, because of course, I don't know with the spirit of collision with soliton gas, but for the modulation instability, of course, we can control the amplitude of the noise.
Okay.
It's even something that we are writing a paper with Amin Shabshub about that. But Anderson localization appears when it's not the wave that have disorder. It is the propagation media that has disorder.
Yes.
Okay. So here the propagation equation is just pure NLS. There is no disorder inside. The disorder is in the wave itself.
Yeah.
Okay? So conceptually, it's difficult for me to make the link.
Okay. Thank you.
Okay, and we have a comment from Benjamin Doyon. There is hydrodynamic diffusion also in soliton gas in principle.
Oh, okay.
Yeah, can I just do? I'm not sure if this is related to the question, but there is the concept of the solitons kind of move around like in the nice picture that you show, and then have go at certain velocity. But because of soliton collisions, there's also some kind of randomness in the way that they move around. Randomness due to the initial state.
Okay.
And that leads to diffusion, actually, and it's possible to calculate the diffusion. So it's a bit related to that.
Okay. Are you going to speak about that in your talk?
So maybe I say a word. I mean, but you can ask me, I can tell you more.
Okay.
If I get there.
Okay.
Thanks.
I guess I would be interested as well, if possible.
Okay, thank you again, and thank you, Pierre. So we're a little bit late, Remy, so don't worry, I will put five more minutes for your talk.